Okay, so this is the second video for the discussion for Lab 3. If you didn't watch the first video where I constructed this normal curve to match this histogram, you probably want to go back and watch that first. The rest of this will make a lot more sense. Watch that one first. What I'm looking to do now, try to clean up, and I'd really like to move this text box if I could. There we go. Let's see. What I'd like to do now is explain the normal probability plot, what the purpose of that is, and again reiterate the purpose of this normal distribution. If a variable follows a distribution that looks like this or this, there's certain really specific characteristics of the distribution that allow us as statisticians to make statistical inferences as to whether something is unusual or not. Like if somebody tosses a coin 4 times and gets heads every time, should somebody accuse that coin of being unfair? Is that unusual, right? And we need probability, the language of probability, to determine with a number what's going to be unusual or not unusual. Okay, so the normal probability plot is going to use z-scores, right? Z-scores or normal scores, all right? Again, they come back to this idea of standard deviation, okay? They tell us specifically how many standard deviations above or below the mean an observation is. So if you take a test in a class and the teacher says to you that you had a z-score of 1, you probably ought to be happy with that, but it might be more helpful for you to know what the mean and standard deviation of the tests were for that particular test. So like if the mean was 80 and the standard deviation was 5, then that means you scored an 85. If they said your z-score was -1, well, that means you're below average. You're probably not happy about that. But if you know the standard deviation, then you know that the raw score would be 75, okay? So if somebody has a z-score of 2 or 3, even if they don't know the actual number, they know they did pretty good because they're above the mean and you're using standard deviation as your relative measure of how far above the mean you are, okay? So here's what the normal probability plot does. It makes a scatter plot, okay? It makes a scatter plot of raw scores and z-scores. So if a distribution is approximately normal, what you ought to expect to see in that normal probability plot, well, I'll let you make your own observation and maybe we can go with it. But remember, this data that we're dealing with heights looks approximately normal, right? From the histogram and then from the normal curve. So we're going to make this normal probability plot, and here's what I'm going to do. I'm going to call this column z-scores, okay? And Excel does have a formula to find z-score, okay? Remember, it's the raw score minus the mean divided by standard deviation. Now, I still have the mean and standard deviation. They're hidden over here, all right? So I'm going to use those. So I want to come over here to this z-score column. I'm going to type in equals, and I'm going to start to type in the word standardized, okay? Because standardized is another standardized score or z-score. They measure the same thing. So I double click on that, okay? And notice what it asks for. It says, what's x? Well, x is going to be the raw score, all right? In this case, it's going to be men's heights. So I click on that. We use the comma, and now it wants the mean and the standard deviation, which I have conveniently tucked away over here from the first go round with this lab. So 177.7453 is the mean, and the standard deviation is 7.183629. Don't worry if you don't go as specific on your rounding as that. So what I ought to expect to see here is a z-score of about a half, I think. This guy's height is 170, or -1/2 rather. This guy's height is 174. The average height is 177. So his z-score ought to be negative. He's going to be below the mean. How much is he below the mean? Well, just by eyeballing it, like 3.7 below the mean, and the standard deviation 7. 3.7 is a little bit more than half. So a little bit, -0.6 or -0.7, something like that is what I ought to see as the z-score, right? He's below the mean, and he's not a whole standard deviation below. He's only about half a standard deviation. So I'm going to press enter, and there we go. I got -0.52 So that means he's below the mean by about half a standard deviation, okay? So remember what we want to do. We want to copy that formula all the way down. I want all the z-scores for all of these heights, right? So if you remember the shortcut here, I'm going to click on this cell. I'm going to hit Control-C. So Control-C highlights that. Now we can scroll down to the bottom, get to that last spot. Remember, hold your Shift key. Is that still highlighted? Not cooperating with me. So I'm in there. I'm going to go Control-C to copy that. I'm scrolling down. I'm going to hold down Shift, click in that cell, and it fills up the whole cell. I'm going to tell it, hey, copy, now paste it. We already copied it, so Control-V will paste all those z-scores, right? So look, his height's below 177, below the mean negative z-score. This person is pretty tall, 193, and the mean is 177. Look, he's 2.2 standard deviations above the mean. That's a high z-score, okay? So now what I'm going to do is make my normal probability plot. It is a scatter plot of raw scores and z-scores, okay? And let's see if we can notice what's going on in that particular plot. So I'm going to highlight height. I'm going to hold down Control. I'm going to highlight z-scores. And then hopefully when I go to Insert, Excel knows that I'm looking to make some kind of scatter plot. All right, so it recommends a scatter plot. Let's go with that. Okay, let's click OK. So I get my scatter plot. Now, again, I don't know why Excel doesn't have a little bit better common sense. Everything happening here in the raw scores is happening between 150 and 200, basically, right? So how about we just look at that, all right? So I'm going to, I want to get on that axis. There we go. So I get to that axis, I right-click. I want to format the axis, and I don't think it's super helpful to look from 0 to 250. What if we just look at 150? You didn't have anybody shorter than that. Up to 210 is cool. That should work. Okay, a little bit better. Okay, so what do I have here? It looks like the points generally seem to follow a pretty straight line. All right, so what we can deduce from this normal probability plot, it's definitely a plot that I like to look at if I want to know if data is roughly normally distributed. These are certainly helpful, but a normal probability plot, especially graphing calculators or a lot of statistical softwares, can make them a lot easier. Like we had to do a lot of the heavy lifting here. I had to calculate z-scores, I had to make a scatter plot. Most legitimate statistical software, you can just, you should be able to click on, your data analysis and normal probability plots there, and you tell it what data to make it from. So it's a really quick way to assess normality. Your box and whisker plot is another way that you could assess normality. I don't think it's in this particular lab, but if I highlight here, let me see, a box and whisker plot. This is another one that is really easy to get. Okay. So again, this axis here, Excel not being super helpful to us. Let's format the axis, and let's again lock in on, let's say 150 to, let's see if they go to 210 again. All right. So notice what I see in the box plot. And the way that the box plot gives your 5-number summary. Looks like there's an outlier here when they plot a point separately like that. So there is one low outlier that falls below 160 and one slightly high outlier. But other than that, what do we see in this box plot? I see symmetry. It's symmetric. I can't see the mound shape to it, but I can see that there's a pretty equal space from the min to the first quartile to Q1. Then there's, from Q3 to the max is pretty equal space. Here's my median living in the middle, equally spaced, okay? So any of these plots, all of them would suggest to me that the heights here, this list of data here, is roughly normally distributed, okay? If I look at the histogram and I see a long tail to the right, that would be a skewed right distribution. I'll do a real quick Google image for you. Let's go images. Okay, look, skewed right histograms. They have a long tail going to the right. Look at that tail. Tail to the right, all right? Skewed right. Look at that, not linear, right? See how these are normal probability plots, z-score versus raw score. But see the bend? It's bending like that. That's going to suggest that it's not a normal distribution. What we want to see is something that seems to be a little bit closer to linear. This one actually is bending too if you look really closely, okay? And then a skewed right box plot. Well, this is skewed left, but unless these are higher numbers. But skewed right, we'd be looking at a long tail to the right, right? This is skewed to the right. Look at these outliers, right? Big numbers that are going to inflate the mean, okay? So keep that in mind as you're working through the labs, and I hope both of these videos make your Lab 3 a little bit easier and better understand why we would need any of these graphs. And so that if we're assuming that a variable follows a normal distribution, our conclusions, our inferences that we make are based on that assumption. If that assumption is not true, then the inferences we're going to make really wouldn't be valid. Right? So it's a pretty important tool for a statistician. Okay, good luck.